Hello. So today's topic is transformation of exponential functions. So remember from last class, you learned that exponential functions look like this, right? Y equals to c. C is some base to the power of x. So today we're just going to add those transformations. And these are the same transformations we've been looking at since the beginning of the course, which is a, b, h, and k. So if we add that into our exponential function, it will look something like this. So we have a in the front, we have our base. In front of the x, we have our b. H is subtracted from the x, and we have k. And just to recall some of the definitions, so a will be in charge of vertical stretch and vertical reflection. B is going to be dealing with horizontal stretch and horizontal reflection. H is horizontal translation. Oops, don't know why I wrote it like that. Horizontal translation. And K is vertical translation. Now, thinking about our graph, I'm just going to draw a kind of takeoff graph, right? At y equals to 0, there is this kind of line, right? There's that horizontal asymptote. So when you think about it, if we're moving the graph up and down, the horizontal asymptote would always move with it. So therefore, k in this particular function also deals with horizontal asymptote. Oops, asymptote. There we go. So let's put this into practice. So we have this function here, y equals to 0.5 for negative 2x minus 6 plus 2. So first off, let's break down the different transformations that we have. So this 0.5, this is a vertical compression. This 4, it's not a transformation, it's actually our base. This is our c, okay? Now in here, we need to be very careful. We need to factor. So we actually have negative 2x plus 3. So we have a horizontal reflection and a horizontal compression. And here we actually have a horizontal translation 3 left. And then finally, we have this last one here, which is a vertical translation 2 up. So I'll actually just write out all those transformations on the side. So we have a vertical compression by half. We have horizontal reflection. We have horizontal compression by half. We have horizontal translation left 3, and we have vertical translation 2 up. And this is also our horizontal asymptote. So now it's a matter of, let's plot in some points, right? But before we plot, let's deal with this mapping business here. So we do know our xy will become, x is going to be affected, it's going to be compressed, reflected, and moved to the left. Our y will be compressed and moved to up. So now we need to think about what are our base values going to be. Now, unlike all the other functions, we actually have a very specific base here. It's not just y equals to cx, because we have a specific c. In this case, that c is 4. So here is our base function. And when you do a quick table of values, we know that some of our key points is 0, 1, 1, 4, negative 1, 1 over 4, and negative 2, 1 over 16. Okay, I'll need to let's move this over here. Okay, because I'll need that space later. So that's our base. So with those points, we can now deal with our mapping. So we have 0, 1. That will basically become negative 3, 2.5. We have 1, 4, which will become negative 3.54. We have 2, 16, which is negative 4, 10. Negative 1, 1 over 4 is going to be negative 2.5 to 1 over 8. And we have negative 2, 1 over 16, which will be negative 2 to 1 over 32. So now we can plot those points in. We already know our horizontal asymptote is at 2, so we could draw a straight line across there to make sure we don't cross it, because remember, you can't cross the asymptote. And now we're just going to plot the other points. So we have negative 3, 2.5. We have negative 3.5 and 4. We have negative 4 and 10. Okay, so it's kind of off the chart already. So I'm just gonna draw a line and connect these guys. And then we have negative 1 and a quarter. No, negative, sorry, not negative 1 and a quarter. Negative 2.5 and 2 1/8. Anyways, that's gonna be, we just know it's gonna be approaching the line and getting really, really close. Ugh. And there we go. So we have this very sharp angle here. So this is how you would graph it. All right. So moving on to a word problem now. So an element has a half-life of 520 years. If there is 100 grams of an element to begin with, determine the equation. So usually with these, it's always nice to draw a sketch just to have an idea of what this may look like. So we know, just to draw a sketch, so we have something that is, we know it's starting at 100 grams and it has a half-life. Half-life, remember, means it's going to get cut down in half and then gets to get down in half again and then half again and then etc. And every time it cuts down in half, it takes the length of the half-life. So when it gets to 50 grams, for example, half is left. That length of time is 520 years. So this is in years and this is in, I guess, grams. So since we know it's a landing graph, then our C value must be less than 1. And in this particular case, since we're constantly cutting in half, we already know C equals to half because we're constantly multiplying our number by half. So we know there's a half here. Now the question is, well, we know it's y equals 2 as well. Now the question is, what are my other values? So remember, before, for a normal graph, or not for a normal graph, but for a graph with no transformations, a exponential graph will cross at 0, 1, right? That is that key point typically for exponential graphs. I'm going to just draw one here. Most of the time, they kind of cross through there. But right now, our graph has moved up to 100. So therefore, we know there's a vertical stretch. So that starting point here is, it's going to be at 100. Now next, we need to think about our exponent part. Now, how often is our number being multiplied by half, or how often is it being cut in half? Well, it's happening every 520 years. So I'm just going to start by putting X here. So we know this should represent every 520 years. Okay, so that's how one way it could be written. But some of you, well, might want to write it a different way, right? You have Y, you know it starts with 100. Well, instead of having X represent how many 250 years there are, I guess you can have, oops, why am I changing back to color? If you want to have X in years, then you'll need to divide it by 520 to know how many times or how many groups of 520 you have and how many times you cut in half. So in this particular case, in my black colored function here, in the black ink, X here represents just years. And my function in blue is group of 520 years. So both ways would work, but if you do write the function in blue, please be mindful that X represents groups of 250, so you'll still, or sorry, not 250, groups of 520, so you'll still need to do the division. So this here is the function that I'll be going with for the rest of the questions here. So describe what the numbers mean. So in this particular case, 100, that's basically your A. This is basically the starting value. And you're going to notice A is the starting value in many cases for exponential functions. Okay. Next, we also have half, and this is basically your base, right? So it's the base, and it's also the, this is to represent half-life, being cut in half. Now, the 520, this is basically your B value, right? And this is representing, I guess, time per half-life. That's what that would mean. Now, knowing this information, we're just going to solve how much of the element remains after 40 years. So in this particular case, this 40 basically is our X, right? Because that's the part in years. So it's just a matter of putting the number into the function. So we have Y equals to 100 half 40 divided by 520. So now I'm just going to punch this into a calculator. And the number I got to is 94.80. Now remember, what does this number actually mean? Well, that's talking about the grams of my element. So grams is the units. And there we go. And that's it for this section.